Hi guys, and welcome to another virtual chemistry lesson where we're going to talk about the forces between compounds, not just within compounds. So sharpen your pencils and get ready to take all of them notes. And here we go. Okay, so intermolecular forces. These are then bonds, as we say, or actually forces between chemical compounds. Remember what we said? International relations, that's relations between countries. So that word inter means something, right? Intermolecular forces, that's between compounds. Here's an overview of the various types of intermolecular forces that we will be covering in this video. We can talk about ion-dipole interactions, the strongest of intermolecular forces. Then we can talk about hydrogen bonds. We can talk about dipole-dipole interactions between polar molecules and van der Waal forces between non-polar molecules. And you can see the relative strength of these various intermolecular forces down here. So the further to the left in this figure, the stronger the type of intermolecular force, though everything's relative, of course. But never forget that what we're talking about are electrostatic attractions. Remember that positive and negative charges attract, and they're going to do this not only within compounds but across compounds. Like this water molecule here is going to tug on another water molecule's charges, and that's how we explain how all compounds really interact with each other. But first we need to make a distinction between full or partial charges. A full charge, we've covered these when we talked about ions. That is when a compound has acquired a complete positive charge, that is, it has lost an electron, or a complete negative charge. And I'm going to change that in real time. So everything's correct. There we go. So a complete negative charge. So we get more negatively charged when we acquire electrons, right? For example, in the reaction between sodium and chlorine, an electron is transferred. Sodium acquires a complete positive charge, a full positive charge, because it has one more proton than electrons. Chlorine becomes chloride and gets one more electron, that it has a total of protons, so it gets one negative charge, like so. Partial charges then. Well, these arise in our dipoles when we have polar covalent bonding going on. Remember the water molecule model we drew? We can also make it like this with the electron cloud, with areas of high electron density and low electron density. In this image, even though we made minus signs and plus signs just to indicate that there's a difference in the charge of this electron cloud, it's very, very important to realize that oxygen does not have a -2 charge or a 2- charge, but that the molecule is more negatively charged on one side, but it doesn't have 2- because it hasn't acquired complete electrons. The additional electrons it has gathered are shared in covalent bonds, so it has to share these. So they're not fully part of the oxygen here. If we look at the hydrogen, they do not have a +1 charge, but they're more positively charged because the oxygen is going to tug on the hydrogen's electron much harder because it has a higher electronegativity. So the effect we're going to notice is that the area in the bottom here is going to be a little bit less electron dense, so it gets a partial charge. So not full charges, but we could say like 0.5 charges or 0.35 charges. These numbers are arbitrary, but I hope you're with me here that we don't have full charges, only partial charges, changes in the electron cloud. We usually denote partial charge not with these big minuses or pluses that I've written out here, but rather with delta plus or delta minus, just to indicate that we have a partial charge. We can do this like this. that we fill out these delta minuses and delta pluses in our various models or structural formulas, just to indicate that we have a partial charge here. Right, so here's our types of intermolecular forces and the strength of their interactions. So ion-dipole are going to be the strongest, followed by hydrogen bonding, dipole-dipole, and lastly van der Waal interactions. When we talk about ion-dipole interactions, well, here we have something with full charges and how they interact with polar molecules. Since we deal with full charges, we expect these interactions to be the strongest when we're speaking about how strongly they electrostatically interact with each other. When we talk about hydrogen bonding, it's molecules with unusually strong partial charges. So they're approaching full charges, but not actual +1 or -1 charges. But they're unusually strong, and it's actually the same as dipole-dipole interactions, but so special dipole-dipole interactions that they are given their own category. Then we have dipole-dipole interactions. Molecules with partial charges are going to attract, and these are called dipole-dipole interactions then. Van der Waal, this deals with non-polar compounds, non-polar molecules. And they are large molecules with temporary partial charges. Then we call it van der Waal forces, and we'll get into what this is. Also, melting and boiling point. The stronger the intermolecular force, the higher melting points and boiling points are observed. Of course, relative to shape and size of molecules and the number of bonds each molecule or compound can form. But as a general trend, we can say that the stronger intermolecular force we have, the higher melting points. Let's start with ion-dipole. This is the strongest intermolecular force we have. And if we're going to have ions and dipoles close to each other, then full charges of ions will strongly interact with the partial charges of the molecules, these polar molecules that are dipoles. As we see on this picture here, we have a model of a water molecule in the middle with its, I've written out pluses and minuses just to indicate these partial charges. Might have been better used delta here, but well. Then we have ions in blue and red here, and you can see that anions are going to be attracted to the positive partial charge of the molecule, and cations are going to be attracted to the negative partial charge of the molecule. And each ion can deal with more than one water molecule, of course. An example that you can remind me to show you how it looks. Copper sulfate is a blue powder. Whenever we take out copper sulfate, it's going to be a pentahydrate. And that is a salt with water molecules trapped within the salt crystals. In order to remove all of these water molecules, to dry this copper sulfate so it's not hydrated, then we're going to need temperatures up to 200 degrees. So that's the temperature we need to separate water molecules from ions in the salt. If we compare this to pure water and how the temperature we need to separate water molecules, then we only need about 100 degrees. So there's a big difference here. And as we heat up copper sulfate, water molecules are going to go away, like this. And the fewer water molecules we're going to have, the more attracted they're going to be to the salt, and we need to increase the temperature higher and higher. So we need temperatures about 200 degrees to get rid of all the water molecules and get just copper sulfate salt at the end. Okay, let's switch gears and talk about hydrogen bonds. These are bonds or forces between polar covalent bonds that contain hydrogen. And these are the same thing as dipole-dipole interactions, but they're so strong that they've given their own category. And we can only get these hydrogen bonds in a few special cases, so these are good to learn by heart. For example, when we have fluorine and hydrogen, and they share valence electrons in covalent bonds, there's going to be a large difference in electronegativity, and we're going to get 1.9 as the difference in electronegativity. When we have oxygen and hydrogen, when these share valence electrons in covalent bonds, there's also a big difference in electronegativity, and we observe hydrogen bond going on. Nitrogen and hydrogen, when they share valence electrons in covalent bonds, it's not going to be as large a difference, but still a very large difference. You can see that this difference in electronegativity between fluorine and hydrogen is larger than 1.7, right? So it's stronger than we would expect for a molecule. Alas, it turns into a molecule. So that's why these numbers I've given you are to be regarded as guidelines, not strict rules that always work. These are the three cases where we observe hydrogen bonds: when we have fluorine bonded to hydrogen, oxygen bonded to hydrogen, or nitrogen bonded to hydrogen. So if you learn these three, that whenever you have a nitrogen and a hydrogen bonded together, or an oxygen and a hydrogen, or a fluorine and a hydrogen, then we're going to have hydrogen bonds. And the strength of each individual bond is going to be stronger because we have for example, fluorine and hydrogen, because they have a larger difference in electronegativity. Fluorine is pulling harder on the electrons here. So the electrons are going to be very close to the fluorine, and this is going to be almost a complete plus charge, and this has almost acquired a complete minus charge. Okay, another thing we need to understand, and we'll get into why later, is that electrons in all compounds are found in pairs, except for when we deal with radicals, but we're not going to talk about radicals in this course. So, as a rule, we find electrons in pairs. Look at this water molecule here, at this image, for example. In each of these single bonds, we're going to have 2 electrons per bond, so these electrons are found in pairs, right? And the free electrons in the valence shell are also going to be found in pairs. Okay, this is a strange rule. Why, you might ask? Well, again, we're going to have to go into orbital theory to explain this, but in each orbital there's room for 2 electrons. So, and when we fill our orbitals, we're going to fill them with 2 electrons per orbital. So we find them in these orbitals with opposing spins, but this is beyond the scope of this course. To simplify this model quite a lot, we can draw it like a water molecule like this, where a line symbolizes an actual bond, and then electrons as dots 2 by 2. And this is sort of a Lewis structure of this molecule. And here we have pairs of free electrons. And with free electrons, I mean electrons not in a chemical bond. And let's talk about hydrogen bonding then. It's between the free electrons and the hydrogen atoms where we have this strong hydrogen bonding occurring. Because these free electrons, they're going to be negatively charged. And the hydrogens, they have, in the case of hydrogen bonding, they have a very strong positive partial charge. There's going to be a strong interaction between electrons and hydrogens here. So we observe very strong bonds being formed. And there's 3 reasons for the strength of hydrogen bonds. First, the large difference in electronegativity. We take the largest differences in electronegativity we can find when we look at our electronegativity tables, and still make, of course, covalent compounds. We have free electron pairs in all of these cases that hydrogen can be attracted to. So for nitrogen, fluorine, and oxygen all bonded to hydrogen atoms, we're going to have free electron pairs with negative charges. Hydrogen is also the smallest atom, right? It only contains a proton and an electron. And if we pull away this electron in a closer to another atom when we form a compound, this proton is going to be unprotected by a shell of electrons, right? So it's pretty much just going to be an exposed positive charge at the endings of these molecules. So at this H here and at this H here, it's just like a plus charge, pretty much unprotected by electrons around it. So it can get really close to these free electrons of other compounds and have strong interactions there. So let's make a thought exercise. Here we have 3 compounds with just nitrogen and hydrogen in ammonia, oxygen and hydrogen in water, fluorine and hydrogen in hydrogen fluoride. Okay, so which one would you expect to have the highest boiling point? Feel free to pause the video here and think about this a little bit. Well, water has the highest boiling point. If we compare them, the boiling point of ammonia is minus 33.34 degrees Celsius. The boiling point of water is, as you probably know, 100 degrees Celsius. And the boiling point of hydrogen fluoride is 19.54 degrees Celsius. So this is somewhere between ammonia and water. Why? Well, even though hydrogen fluoride has the strongest interactions for each hydrogen bond, we can investigate this further and draw free valence electrons as pairs. So we draw these Lewis structures and we'll get this answer. And I would like you to pause this video and draw these in your notepad and see if you get these right. So I want you to draw these molecules with bonds as lines and where you show the free electron pairs. So pause the video and do that now. And I'll get on with this. So you will hopefully have gotten something like this. If you know your Lewis structures. So let's think about this a little bit. So we have partial charges here, and we're going to have 3 positive partial charges on these hydrogens in ammonia, and 1 negative side where we have the free electron pair as well. If we compare with water, we're going to have 2 positive partial charges and 2 negative partial charges. And if we look at hydrogen fluoride, we're going to have 1 positive partial charge and 3 negative partial charges. Okay. So I want you to think about how many hydrogen bonds can each molecule form. Well, in the case of ammonia, we have 3 partially charged hydrogens and 1 free electron pair. In oxygen, we have 2 partially charged hydrogens and 2 free electron pairs. And in hydrogen fluoride, we have 1 partially charged hydrogen and 3 electron pairs that are free. This means that if we're going to compare ammonia molecules and look at how they interact with each other, we can only form 1 bond between 2 molecules, right? Because we can have one of these one hydrogen being attracted to the free electrons here. When we talk about water, we can have 2 partially charged, we can have 2 hydrogen bonds formed between 2 molecules. So, and we're going to look at that closer. But that's because they have more than one of both types of these partial charges. Hydrogen fluoride. Here we have one hydrogen bond being formed again, because we have 1 positive but 3 negative. But we only have 1 positive to deal with, so if we're going to bond with another one, it's only 1 hydrogen bond between 2 molecules we can have. And I'm actually going to show you a simulation of water in 3D. Let's see. Right. So here we have a bunch of water molecules, and I can spin this around like so. So if we have these water molecules and we simulate theoretically by advanced mathematics how these would interact with each other, we'll see how they will aggregate, how they will form a structure together. And they're going to lump together like so. And you can see here, if we look at this guy right here, it has formed 3 different 3 different bonds to 3 different to 3 other water molecules. with its positive charges. It also has the possibility, no, sorry, two of these hydrogens are pointing down to negative partial charges, and the hydrogen from another molecule is pointing towards the negative partial charge of this molecule. So you can see that all water molecules here can interact with several of the other type more easily, so they can really aggregate together strongly. Okay, a few words about water. Water is a very special compound and it's essential for life on Earth. And it has some very interesting properties we can get into. First and foremost, it has lower density as a solid than as a liquid, which few other compounds have. So it's going to expand when it freezes, right? Water also has surface tension due to the hydrogen bonds they form. So it's actually possible to have a larger volume of water in a glass than the actual volume of the glass, because some water is going to be stuck together with high surface tension on the top. And surface tension is essential for plant life, for example, as they pull up water to the treetops using this method. Water also has a high heat capacity. We need to add lots of energy in order to increase the temperature of water by 1 degree. This means that it's a fairly stable compound and doesn't change its temperature fast. And since living organisms mainly consist of water, this makes us sort of stable in an environment where temperature changes rather rapidly. So a very good compound. Okay, let's switch gears and talk about dipole-dipole interactions. Well, they work in the same way as hydrogen bonds. We have partial charges that are attracted to each other. But these interactions are weaker because we're going to have shielded off partial charges. But let's look at the nitrogen oxide here. It's actually nitrogen monoxide, to be fair. So this nitrogen here has a positive partial charge and is therefore attracted to the oxygen's negative partial charge, and so on. So they can interact with each other fairly well, but not as well as compounds with hydrogen bonding. Finally, we're going to talk about van der Waal forces. And this is probably the most complicated of them all to understand. So in order to understand these fairly well, we need to consider all electrons in a molecule. For example, this molecule here. 1, 2, 3, 4, 5. So this is pentane. And we'll get into how to name these in the organic chemistry section later. So the easiest way to do this is to think about a cloud of electrons, because otherwise it would be very, very hard for us to draw out all the electrons and then consider them all. That picture is fairly complicated. So let's just make a model of this, where we model the electrons as a cloud, which we have done before. So, but just as a thought exercise, this molecule, it is going to contain a total of 42 electrons, because we have 5 carbon atoms in here. They each have 6 electrons, so that's 30 in total. We have 12 hydrogen, which each have 1 electron, so that's 12. Then we can sum this up and get 42 electrons in total. So it's 42 electrons that we need to think about, which is fairly complicated. So just think about a cloud of electrons surrounding a molecule. And that's how we do when we do computer simulations of these things as well. So with that model, we're going to talk about how van der Waal forces actually work then. Well, they are the weakest intermolecular force, but we have a trend that the larger the molecule is, then it's going to have larger electron clouds, because we have more atoms and more electrons to deal with. We can have compounds which only have van der Waal forces, unpolar compounds with higher boiling points than water, but then they have to be way, way larger molecules. So relative to size, these are the weakest ones. But size also plays a huge impact here. And van der Waal forces, they arise due to temporary dipoles in the electron clouds. So dipoles, remember, that's when we have a shift in where we have the electrons and protons. So we get these partial charges. In this case, we're going to have temporary partial charges. So we imagine this as a electron cloud again, and we're going to have a part of this electron cloud that's going to be a little bit more negative, and a part of this that's going to be a little bit more positive for a very short period of time. But during that short period of time, it can interact with another molecule with similar temporary partial charges. And how does this work? Well, first we need to think about how could we possibly get temporary dipoles, because this compound here, which only contains hydrogen and carbon, the difference in electronegativity is low. It's 0.4 if I recall. So we don't expect them to be dipoles in any way. So how would they get these temporary dipoles? Well, you need to think about liquids or gases and how particles can move in liquids and gases, and whenever particles can move, they will collide. And this moves so fast it's impossible to imagine, but we're going to slow time down a lot with our model and just think about what happens when two molecules collide. So here we have pentane with an electron cloud, and another one is going to come from over here as well. So when these guys collide with each other, like so, well, then we're going to have electrons on this guy and this guy get very close to each other. They're going to repel, because remember, electrons don't like each other, except for when they're in pairs. I know, it's a bit tricky. But minus doesn't like minus, it's like magnets, right? So these electrons are going to be displaced. They're going to be repelled and move and be shifted into the sides of each molecule. And we're going to get something like this, that we're going to have a vaguely more concentrated negative charge on this side and a vaguely more concentrated negative charge on this side and a vaguely more positive charge on these sides that collided. And then they can have these interactions, but this is for a very short period of time, but they collide so quickly and so often that this is going to have a net effect, an overall effect that we observe when we look at these compounds. So that's what we observe during a very short time period. But this can actually play a substantial role. If we have very large electron clouds for very large molecules and they collide, then we're actually going to have stronger interactions than we have in water. So it depends on the size, of course, but relative to size, these are the weakest intermolecular forces we have. And that's it. I hope that was enlightening, and we'll get into how to draw molecules and think about how the electrons are placed in molecules when I see you in class. But until then, have a great time, and I'll see you soon.